So peeps, another day and another component video for you beautiful people out there. So what we're going to go over is VFDs, variable frequency drives. Why would we use these over contactors or stop start? So contactor, you've got that sheer initial energy coming in as soon as that contact made, and a soft start, it's great, it brings it in softly, but you still got no control over the top peak. With a variable frequency drive, we can control it, energy efficient, and they're just great. Let's get on how they work. So we've got three sections to our VFD. We've got the rectifier section, this has got our diodes in. We've got our filter section, that's our DC bus, and then we've got our inverter section. So we've got our three phase coming in with our diodes, then we've got our DC bus with our capacitor, and then we've got the inverter section. That's where the magic happens, and that sends out the frequency and voltage signal to your AC motor. So we've got our rectifiers section. So what we've got is we've got each phase coming in on one leg with your diodes, and them diodes are only going to allow voltage one way. Well, we all know that AC voltage likes to oscillate. So what you're going to see is you've got your sine wave here. This is what you're going to look like as you come your voltage incoming. But as we know, bridge rectifiers, this is like a three-phase kind of bridge rectifier. So as you can see, that voltage is going to be coming in, flowing one way, but it won't allow it to flow back. So if you've never seen one, this is a bridge rectifier. So you can have your diodes in a certain pattern, and that's just allowing the AC to only go one way. So you'll have AC in, DC out. Please excuse me, I didn't do art at school, and that's obvious. Them sausage fingers can only do certain things. But you'll have your AC in on the left, and your DC's coming out on the bottom. With your three phases, they're going to be 120 degrees out. This is only a sine waveable single phase, but you'll get the gist of it. So then we'll move on to what the DC bus side does of it. So we've got a sine wave coming in, and now what that's going to do with them diodes, I'm just going to draw the next wave form when it goes over to the DC bus. And even on a single phase one, you will have the capacitor to be smoothing out that waveform, because as you're going to see, you're just going to have the top peaks on the next waveform. So our filter section is where we're going to take on the DC now. This is what a waveform is going to look like now, and all you got is the top peaks. And with our capacitor now in line, what that's going to do is that's going to discharge some voltage every time we have so now every time we have a drop in the peak of the voltage, that capacitor is going to discharge some voltage, and that's going to give you your typical DC voltage, the line that you would normally see. So now we're going on to the inverter section. Now this is where the magic happens, because this is going to take that DC voltage and it's going to convert it into something you'd normally see on an AC waveform. And now we're going over to where the magic happens, the inverter section. So what this is doing is this is taking the DC voltage that we're now getting across from the rectification and the filter section. And this is going to interpret into what this motor is going to see as an AC waveform. So this section's got a series of, on each phase, of IGBTs, which stands for insulated gate bipolar transistor. Now these are brilliant for taking high loads and switching fast. Just think of these as small PCB relays. And that's going to be switching our DC voltage on and off in a high-speed controls. So we've got our waveform coming in now, and what that's going to be doing is injecting DC voltage, and I'll just one little artifact here will show you. So what it's going to be doing is, so what it's going to be doing now is shooting in DC voltage in pulses, which are going to be short bursts, and then you might get a longer burst of DC voltage. And then it'll go to a short burst again, and then it's going to switch the polarities, and then you get short bursts, and then it might get a longer burst of DC voltage, short burst, longer burst, and then this is going to repeat itself, switch from polarity, short burst of DC, and then you get a longer. And this is going to help us change the frequency in the long run. Because what this will do, and this is going to change the bandwidth of the DC, the pulses coming in, and this is how we're going to change our hertz. So as you can see now, this is looking more like what you normally would see in an AC waveform. Now your motor's not going to recognise it, it's not AC. What it's just going to see is it's going to see them pulses and the paralysis. And that's how we change our hertz, by the pulses, widths and the time between them. So what you can actually see in real life is, in the top left is actually the AC waveform coming in, and your bottom right is the DC imitation waveform on the bottom. So let's get into the juicy part everybody loves, the testing. So I would always check you got your right settings on the drive first. You want to be checking your maximum voltage, your minimum voltage, your maximum hertz, your amps, everything that your settings would need to be. So getting into the terminals now. So if you've got overload up there, I would disconnect your tails for your motor. You want to be checking your IRs on your cable and on your motor, because that's going to be more on your motor side of it, overload. So what we want to be checking is that we've got our correct incoming voltage. So we want to be going across all three phases. So we want to be seeing that you've got correct voltage there. We're going to be testing our DC voltage. Now this wants to be 1.4 times your incoming voltage. And then we're going to be checking our voltage coming out and our hertz as well. So with my meter set at AC, I'm going to be checking my incoming voltage. So this is just a single phase one, but you would be going across all three phases. And I've got 230 there, so I've got good voltage coming in. So next, changing out my multimeter to DC, I'm going to be checking my voltage on my DC bus side of it, which is these two terminals down here. And remembering, this wants to be 1.4 times what your incoming voltage is. So I've got 325 volts there. That's roughly about right. So that's all good. So back to AC. Now we're going to check our voltage coming out on our tails to our motor. So what you can do is on these drives as well, is you can get your outgoings on your screen. So I'm going to put that into drive now. And as you can see, it's running at 30 hertz. And I'm just going to put it through to voltage. As you can see, that's about 122 volts. But my meter sees 158. So what these some of the flugs have got, it's got a low pass filter. So that's using a resistor and a capacitor in series, and that's going to allow us to see the average of the bandwidth, because what we've got to remember is that's pulsing DC voltage, so our meter's not really going to see a true reading, but with a low pass filter we can take an average of that. So there's still some discrepancies, but you can see that's dropped down now closer to the voltage. So if you wanted to get down to the nitty gritty of the testing, I would suggest getting one that has a low pass filter in it. And then you can check your hertz as well. That's important, because that's actually what controls with the voltage of the motor itself. So you want to be checking that compared to what your drive's putting out. And as you can see, we've got correct here. And what you want to see is with the hertz going up and down, your voltage will go up and down with roughly about the same time. So if you add it, to make it easy, if you add it on 10 hertz and you put it up to 30 hertz, your voltage at 10 hertz should be about 3 times the same as what it is at 30 than it is at 10. And that's all checking out good. So what we've checked is we checked our incoming voltage, our DC bus, and our hertz and voltage coming out. So we're going to do some dead testing now. So with dead testing, you want to ensure that all power's been isolated to your drive. So I've just turned the power off, and as you can see, that's gone under voltage now. But there is a big important factor you've got to realise is you've got to check that you've discharged all your DC voltage from your DC bus side. And as you can see, there's a little charge light there. So I'm going to wait till that discharges, because that will have stored energy in the capacitors. So what we're going to do now is we're going to do a diode check. So what we want to do with this diode check is we're checking the volt drop over our diodes and our IGBTs to ensure that we're getting correct flow. This is ensuring we're getting correct flow of power across our circuit. Because remembering, with the DC side it should only be going one way, and with our IGBTs it should only flow one way as well. So they've got diodes in their circuits. So with my negative lead on the positive side of the profit bus, I'm just double checking I'm discharging. What a good boy. Safety first, kids. So with my voltage now dissipated, I'm going over to the diode section, and you'll get diode on the screen. So what I'm going to be doing is I'm going to put my negative lead on my positive side of the profit bus, and I'm going to be going across. So what you want to see is about really 0.3 to 0.4. This is okay at 0.5, and you also want to balance across all of the three phases. As you can see, we've got a nice balance across all of them. And then the next one, I'm going to go positively to my negative side, and again we want to see a nice balance row of numbers across all three phases. Now checking out okay. So if you've watched to this end and I haven't bored you to tears, you beautiful people out there, you're ledge to prove.